So welcome back to the continuation of our tutorial series on deploying a machine learning model on Kubernetes. So in this part, we will be seeing how to deploy the ML services on Kubernetes. So we'll be writing the Kubernetes manifest file for like deployment, service, config map and PVC. And also we'll be trying to apply the Kubernetes configuration and we will verify the deployment at the end. And then we'll also implement autoscaling with HPA, like understanding like horizontal pod autoscaler, what it is, and then also you'll be configuring and applying HPA to scale the ML service. And finally, we'll be testing autoscaling under the load. Successfully trained our model, and we have just saved the model in disk, and we have tested the model locally by using the FastAPI endpoints, and then we have just built a Docker image with this FastAPI application, and we have tested this locally as well, and we have pushed this image as well to the Docker Hub registry, and now it's available globally for to deploy with Kubernetes. And it's time for Kubernetes deployment. So I really want to give you a recap. Kubernetes is a container orchestration platform that helps us to automate the deployment, scaling, and management of containerized applications. So in this project, Kubernetes is used to deploy an ML service API that serves predictions. The service should be like scalable, reliable, persistent, and exposed. So what is meant by like scalable? When more instances of services can be created automatically based on the demand. And then when it's reliable, the service should keep running even if some ports fail. And when I say persistent, the trained ML model should not be lost when the container restart. And also exposed, the API should be accessible outside the cluster. So for this project, we do have 5 key configuration, Kubernetes configuration that works together to deploy the ML service in structured way. So we start with like persistent YML here. It ensures the persistent storage for the ML models. And we have our config map, which stores the configuration variable for ML services. And we have our deployment file, which defines how the ML service runs, the containers, replicas, probes. And then we will be having our service YML, which exposes the ML API externally using a load balancer. And finally, we have our HPA, when it's a horizontal pod autoscaler, which enables the auto scaling based on CPU usage. And we have our Prometheus YML for to like monitor the ML service using Prometheus. So persistent storage, which just creates the persistent volume PV and persistent volume climb, which is PVC, and ensures the ML model file is stored permanently even if the pod restart. And we have our configuration management done through like config map YML, which stores the environment variable like model path, logging level separately from the application. So this makes the ML service easier to configure and update without changing the code. We have a deployment file, which is for to deploy the ML service. It just defines how the ML model API runs inside Kubernetes and specify container details like resource limits, health checks, and storage, and ensures 3 replicas of the service for high availability. And then we are exposing the service using a service YML, which creates a load balancer to expose the ML API outside the Kubernetes cluster and allows external user to send request to the API. And finally, we have autoscaling the service, which is done through HPA YML, which automatically increase or decrease the number of service replicas based on the CPU usage, and ensures the API can handle higher traffic efficiently without wasting resources. So let me dive deeper into this each file to give you an insight of what each line in these files are doing. So let's start with persistent YML. So as I said, like persistent volume, which is PV, and persistent volume climb, which is PVC, which ensures that the ML model file is stored persistently across container restarts. So it just creates the persistent volume climb PVC named model storage, you see here, and it just requests for 1 gigabytes of storage, and it's only read write once mode, which allows the storage to be mounted by only one node at a time. And coming back to like persistent volume here, which defines the actual storage, the persistent value named model PV, and it specifies the 1 gigabytes of storage capacity, and it uses the host path MNT data on the Kubernetes node as storage and binds to the PVC model storage, to this. So why we need this? Like if the pod restarts, we don't want to lose the trained ML models. So this ensures the model remains available. So this is the purpose of the persistent volume file. And let's see the config map. The config map just stores the environment variable for the ML services. So we have created the config map named ML service config, and it just stores the environment variable like model path, log level, maximum occur. So model path is the location of the ML model file. So in our case, it's inside models directory. And then we have our information level logging, and then maximum worker, it's the number of worker thread that the ML service can use to process incoming requests concurrently. So in our case it's 4. The service can process up to 4 requests in parallel instead of handling them one by one. So this improves the performance and ensures faster response time when multiple users sends the request to our application. Why we need this file? This allows the ML service to be configured dynamically without modifying the application code. See the deployment YML. So this file starts with API version, which is app slash version 1, which defines that we are using the app API version 1, which requires for managing the deployment. And next we have our kind deployment, which indicates that this file defines the deployment, which is responsible for creating and managing multiple replicas of our ML API. And under metadata, the name ML service sets a unique name for this deployment, making it easy to reference. And the label section assign application ML service as a label. So it just allowing other Kubernetes components like services to identify and communicate with this deployment. And again, specs section, which defines the main configuration of the deployment. So inside this, we have replicas is 3, which ensures that 3 identical ports run at all times. And if port fails, Kubernetes automatically recreates it to maintain the availability. So we have our selector match labels, which ensures that only ports labeled with application ML service are managed by this deployment. And then we have our template section, which defines how each ML service port should be configured. So under metadata label here, the label ML service, which ensures that the ports created by this deployment match the service selector, which we will be configuring in service YML later. And inside the specs section, here we have container. So we define the main container that runs the ML model API. The name ML service, which just identifies this container, while image from the repository. So this is the repository that where we have pushed our image, and we will be using this image. So this image contains our FastAPI-based ML model service. And the port section here, which exposes the container port to 8000, which matches the port on which our API is running inside the container. Next, we have our env, which loads the environment variable from the config map in the config map YML that we saw earlier, just making the deployment configurable without modifying the code. So this allows settings like model path, log level, maximum workers to be managed dynamically. And we have our volume mount. This section mounts the model storage volume at models, ensuring that the ML model file is accessible inside the container. So this volume is defined at the bottom of the file under volumes. So which reference a persistent volume claim that we have declared in persistent volume earlier to store the model persistently across port restart. And we have our resource. This section sets CPU and memory limits for the container. So the request defines minimum guaranteed resources. So in our case, it's 512 megabytes and 500 millicore CPUs. By limits here, which defines maximum allowed resources, which is 1 GB memory and 1000 millicore CPUs. So this prevents overloading the node while ensuring the smooth operation. And we have our readiness probe and liveness probe are critical for health checks. So the readiness probe pings /health, You remember that we have defined earlier with our API endpoint to check if the application is ready to accept the traffic, which will be helping the Kubernetes avoid sending traffic to unhealthy ports. So the liveness probe, which ensures that if the application becomes unresponsive, Kubernetes automatically restore the container to recover from failure. And finally, we have our volumes. This section defines the model storage volume, which link to the persistent client that we have declared in persistent YML. This ensures that even if code restarts, the model file remains available. So basically, this deployment file just creates and maintains 3 ML API ports as we have defined replicas as 3, and it uses the Docker image that we have pushed in the Docker repository here to run the API and exposes the port 8000 to serve requests and mount a persistent value model storage for ML model files and just loads the environment variable from config map, and then it defines the resource limits to ensure the efficient usage of cluster resources. And finally, it just uses the health check to restart failed or unresponsive ports. The horizontal pod autoscaler, which is HPA configuration, which is defined in HPA YML here. It's used to automatically scale the number of ports running in the ML service deployment based on CPU usage, and it also ensures that the ML model API can handle varying levels of traffic without manual intervention. So this file starts with API version here, which specifies that this resource is part of horizontal pod autoscaling API using version 2 to automatically scale ports based on metrics like CPU or memory. And then we have kind horizontal pod autoscaler, which defines the type of resource, specifically the horizontal scaling of ports here in our case. And then we have our metadata. So the name of the HPA service is ML service HPA, which gives the horizontal pod autoscaler a name, and it can be so that it can be easily identified in a Kubernetes cluster. And we have our spec section here. It just defines the scaling rules. The key elements here is the scaling target ref. So it just specifies that this HPA should scale the YAML service deployment. And API version here, which is app/version 1, and kind is the deployment. It just indicates that target is a deployment resource. The name ML service, which refers to the specific deployment for the ML API. And the scaling behavior is controlled with minimum replicas, which is 3 in our case, and maximum replicas, which is up to 10. So this means that Kubernetes will ensure that at least 3 ports are running and can scale up to the maximum of 10 ports based on load. So if the system detects higher CPU usage, it can spin up more ports to handle the demand. And finally, we have our metrics section, which defines the resources to monitor for scaling. So in our case, it is monitoring CPU usage. The metric type is resource in our case, and the resource being measured is CPU. The target section, which specifies how the scaling decision is made based on CPU utilization. And then the type utilization here, it just means that Kubernetes will scale the ports based on how much CPU is being used relative to the requested CPU resources. And specifically, the average utilization here is set to 70%. So if the average CPU usage across the ports exceeds 70%, then the Kubernetes will increase the number of ports to distribute the load. So if CPU usage falls below 70%, it will scale down the number of ports. So basically, with this file, we can automatically scale the number of ports based on CPU utilization, and it just starts with 3 ports and can scale up to maximum of 10 ports when needed. And then we'll be using a CPU utilization as a metric for scaling, targeting an average utilization of 70%. So ensures that the application can handle traffic spikes smoothly and optimize the resources usage by scaling down when demand is low. So this is how our ML model API application can automatically adjust its resource allocation, guaranteeing performance during varying workload. So now we do have our all Kubernetes configuration files ready. So it's time to deploy it. So let me open the setup guide. So we have to start deploying these services. As I have already showed you, we have already start our pod machine. It's running currently, and our kind cluster is running as well. So as I have showed, like our Podman machine is running and our kind cluster is running as well to launch the kubectl, and I have added the kubectl extension in the Podman as well. So we are like ready to apply our deployment with kubectl command. So let's deploy the project and verify everything is running as expected. So first start with deploying the persistent volume climb and persistent volumes by doing kubectl apply. The file name is inside. Okay, it's in our case, it's here persistent YML. Okay, so let's deploy it. So before we deploy our ML services on Kubernetes, we need to like set up our environment properly. So this involves setting up Podman machine like as a container runtime and also a kind cluster for running Kubernetes locally. So Podman, we have already do start our Podman machine in the beginning of this tutorial. We have did like init and then we did Podman machine start, and our Podman machine is running currently. So now it's time to create the kind cluster. So it's in progress. So if you see, it's running now. Podman is using kind cluster that we have created as a context. So alright, now that our environment is set up, it's time to like deploy our ML service on Kubernetes. So in this step, we'll be applying our configuration, deploying our application and setting up monitoring with Prometheus and verifying that everything is running smoothly. So let's get started. So first of all, create the persistent volume. So first we need to create persistent volume and persistent volume climb, which is PVC, to store our machine learning model artifacts. And then we have to apply our config map. This will store the environment variable like model path, logging level and worker configuration for our ML services. So you have already applied it. Let's go to Kubernetes panel here and go here to the config map. So you see here it's successfully created. So now let's go here to the persistent volume climb. So with read write once mode, it have been created successfully as well. So if you see the service and deployment is empty, that's normal. We haven't yet create our deployment or services yet. So now let's apply our actual application. So along with its service and horizontal pod autoscaler, which is HPA. For to do that, let's do kubectl deployment. Apply deployment.yml. So now it says like the deployment is created. So this will spins up our ML service pods and ensure they restart if they fails. So you see here it's completely saying like unavailable. That's completely normal because service is not running it. So we need to expose our application with Kubernetes service. For to do that, kubectl apply service.yml. So now it's created as well. So this allows other applications and users to access our ML services via a stable endpoint. So you see it's just deployed with load balancer with port 8000. So finally, let's enable our auto scaling so our service can automatically scale based on CPU usage. For to do that, kubectl apply hpa.yml. So this set up our horizontal pod autoscaler, which will increase or decrease the number of running pods depending on resource usage. So now you see our deployment is available. So now that everything is deployed, let's verify that it's running correctly. To verify the deployment, we can check the deployment status using kubectl get pods, which will check for running pods. So if you see, we can see a list of running pods. If any pod is stuck, crash loop back off or bending status will be displayed. Okay, so we'll need to troubleshoot it, but in our case it's running successfully. So and then check the services. So kubectl get svc. This will confirm that our service is properly exposed and accessible. So look for the external IP or port mapping. So it's completely normal for an external IP to show as bending when running kubectl get svc on local Kubernetes cluster. like a kind or minikube. So why it's happening? Like load balancer service requires a cloud provider. So when we define our Kubernetes service with type load balancer, Kubernetes expects to request an external IP from the cloud provider's load balancer, like AWS ELB or Google Cloud Load Balancer or Azure Load Balancer. So with the local setup, there is no cloud provider. So Kubernetes cannot like provision an external IP, leaving it as pending. Let's check HPA, Horizontal Pod Autoscaler, using kubectl get HPA. So this ensures that our autoscaler is set up properly and will scale ports based on CPU utilization. As you see here, so now, once our ML services is deployed, we need a way to interact with it. So if you are like running Kubernetes locally, we can use kind or minikube. As I said, we will be using kind. The service might not be directly accessible from our machine. So to resolve this, we can use port forwarding, which allows us to like access a Kubernetes service on a specific port from our local machine. For do that, we can do like kubectl port forward deployment slash ML service with the port. So if you see kubectl port forward, what it will do is this command will set up a local network tunnel between our machine and a running Kubernetes pod or deployment, and deployment slash ML service, which this will tells Kubernetes that we want to like forward port for the deployment named ML service. And we have 8000, which maps to 8000. This means the first 800 is the local port on our machine, and the second 800 is the container port inside the Kubernetes pod. So once we run this command, like we see, we can make any request to HTTP localhost 8000 on our local machine will be forwarded to the ML service running inside the Kubernetes cluster on port 8000. So basically, when we like deploy the ML services in Kubernetes, it runs inside a port that is assigned an internal cluster IP, right? So without port forwarding or an external load balancer service, we can't like directly access these ports from our local machine. So the port forwarding sets up a temporary connection that allows us to like interact with the service as if it were running locally. So this will helps in like local testing, debugging, and avoid like external exposure. So once our port forwarding is active, like as you see here, we can test our ML service using curl, or you can test it directly in the web browser by launching the local host. So now let's check the service is running. For that, let's do curl with the text to predict. So we got the prediction from our deployed service. So as expected, we get a status as success. So the service is running smoothly. So let's check the health of the service. So the status is healthy. So everything worked as we expected. So we are in the end-to-end tutorial on like deploying a machine learning model on Kubernetes with auto scaling and monitoring. So far we have like see the overview of the project and also building a machine learning model and APIs, and also containerizing it with Podman, I mean the Docker, and we have also set up our Kubernetes cluster and deploying the ML services on Kubernetes. And also we have implemented the auto scaling with HPA. So in our next part, we will be seeing how we can just set up monitoring with Prometheus. So we will be configuring the Prometheus to scrap ML service matrices and accessing the Prometheus dashboard. So let's see you all there.